Hello everyone, I welcome you all for this presentation which is based on one of the advanced machining process which is electrochemical machining. And this presentation we started in the from the last video, and in the previous video we have discussed about uh, the principle on which this electrolysis electrochemical process is based. Okay, so that is electrolysis principle or Faraday's law. We also discussed about the reactions that takes place at the anode and the cathode part. Okay, when we are taking a simple water or a salty water, we discuss both the cases. Okay, so that ion which is releases from the anode, that will react with the ions, negative ions of the cathode, so that react with each other and make the sludges. Okay, so that we have already seen. We also discuss about the characteristics. Okay, that characteristics of electrolysis. Okay, so what because one of the function of this electrolyte is the it creates the circuit between the workpiece and the tool. So that is one of the main function for that, what characteristics we have required. So that we have already seen. Also seen the properties of the ECM tools, which we are using during this process, electrochemical process. So that tool properties we have already seen. We also discuss about the parameters. Okay, so what parameters we are using. So these things we have already seen in the last video. In this video we are going to discuss about the one of the most important parameter of this process, or in all the conventional as well as non-conventional processes we will discuss that. So that is MRR, that is material removal rate. Okay, so that we will discuss in this video. Also we'll discuss about the feed rate and flow analysis. Okay, so these things, these three things we will discuss in this video. In case we'll get the time, then we'll also discuss about the numerical problems. Okay, that examples or the numerical problems that has been asked previously in the GATE examination. So let's start. ECM system analysis, or just we can also write the topic like making of material removal rate, MRR. Okay, but here what I have studied from the book, so that is written ECM system analysis only. So I have written the same. Okay, so as per the Faraday's law, what we have seen, that material which is depleted from the anode part, or the material which is removed from the workpiece, that M is directly proportional to the one thing which is which is directly proportional to the two things. First is charge, that is I, and ratio, that is A by V. Okay, which depends on these two parameters. So Q is basically the charge. Okay, in this definition also you can see in this sentence, that is Q is basically the charge, and A by V is the ratio. We call it as the electrochemical equivalence. So when we'll remove this proportionality sign, M will be equals to Q into A by V into 1 by F. So when we are removing this proportionality sign from here, we are taking 1 by F as a constant. So F is nothing but it's a Faraday's constant, and its value is 96,500. Fine. Up to this we have already discussed, and we also discussed that this Q is directly it is equal to I into T, that how much current we are passing to the uh, uh, to create the potential difference, and T is the time. Okay, so that charge is equals to I into T. So when you put this value, this will be I into T into A upon F into V. So this is the amount that is depleted, or the material which is removed from the anode part. So that we have up to this equation we have already studied in the last video. So this is one thing. Another thing is uh, this is basically the system we are considered, that this is a container, and over that electrolyte is filled. This is the two electrodes, one of them is workpiece and another is tool. So this anode we are making as a tool. So this is positive, and this is cathode, tool, that is cathode, that is negative. So the positive ion that releases from that anode, and negative ions which is released from the electrolysis. By the way, the negative ion should be released from the cathode part, but the one of the property that we are using from the in the tool as well as and the electrolysis, that before start releasing negative ions from the cathode, means tool, the electrolysis itself releases the negative ions. Okay, so that negative ions which releases from the electrolysis, that will react with each other and that makes the sludge. Okay, so that sludge is nothing but it's a wastage, so that deposited at the bottom part of this container. So this was basically the principle. And now this MRR we are defining for one more term, that is whatever the current that we are supplying to create this potential difference. If I is the current that we are supplying, then whatever the heat is generated which releases the um, material removed, whatever the heat is generated, okay, that is directly proportional to Hg, which is heat generated, that is equal to or directly proportional to whatever the heat is absorbed by the electrolysis, means that will be 100% transferred to the electrolysis. That is only the principle, means that is only the terms that we are using for this. So the second sentence which is written over here, that is MRR in ECM for 100% current efficiency. So the meaning of this is whatever the heat is generated, that heat is directly absorbed, completely absorbed by the electrolysis. That is only the meaning of this sentence. Okay, so I think it is clear to you. So next is this equation, that is m is equals to I into t into a upon f by f into v. So I is the current, t is the time, a is the atomic weight, f is the Faraday's constant, and v is the valency. Now this is basically the amount that is dissolved in the electrolysis, sorry, electrolyte, or the amount or the material which is removed or the depleted from the anode part. So that is in gram. Here we are calculating in gram. So the MRR will be equals to that material removal rate will be equals to mass upon how much time this material is removed. Means when we are supplying this, as I told you that we are making it for 100% current efficiency. So that mass, how much amount of the mass released when we are continuously supplying, means how much supplying time we are supplying this current. So within that time, how much amount of the material is removed. So that is basically the MRR. Okay, now one more thing is whatever the material removal rate formulas or we have discussed previously in the conventional machining processes. Okay, we always calculated as a mm cube per time. This time can be minute or this volume per time, or we can say, okay, this is volume per time. So now this volume we calculated in either mm cube, okay, meter cube, centimeter cube, okay, and this time is in minute or second or hour, whatever it is. But here the term that we are using is that is in gram, or that is in second. Okay, second or minute, second only. Okay, so this MRR whatever I have written over here, that is m by t, will be gram per second. Okay, so now please keep in mind, because this unit is very very important, that is gram per second. Why? Because if you will think about that mks unit, then all the units will be in dimensions are in mlt. Okay, where m is the mass, l is the length, and t is the time, whether this is in kg or pound. This is in means length, which is like meter, centimeter, or mm. This is time, minute or hour or second. But like if you will talk about ampere, sorry, current, that is in ampere, so that is completely different from mlt. If you talk about the f, that is Faraday's constant, and that is calculated in coulomb, so that is again completely different from mlt. So it will be very difficult to you calculate at the end the unit of this mrr here in this process. So please keep in mind that the MRR which is calculated basically in the first equation, that is m by t, is given as gram per second. Okay, so this is very very important, because in the competitive examination, the questions which is asked, like if you are talking about a gate, then this is sometimes nowadays it's a fill in the blanks question has been asked. So means approximately answer should be reach, we have to reach to that. So that can be possible only when we have to know what is the unit of that exactly. Okay, so the next is that we have already discussed, that is MRR equals to m by t, that is in gram per second. Next is I'm just putting the value of this m over here. So this tt will be cancel out, and the final remaining will be I into a upon f into v, that is gram per second. Okay. Now one more thing is, as I told you that in the conventional processes we discussed in volume per time, and that volume we calculated in meter cube, cc, or mm cube. Now here also we can convert this into mm cube or cube per second, or meter cube per second. What we can do is we can divide this ia, we can divide by rho, that is density. So the density can be represented in kg per meter cube. Now the one more the important thing is this kg per meter cube. So this is in gram and this is in kg, so either we have to convert this into gram or we convert in this kg. Okay. So that we have to see accordingly, and at the end we will get this in meter cube per second. Okay. So the next will be, so the next will be MRR, that is dividing with the rho, that is I into A upon rho into AF into V, that is meter cube per second. So this is MRR in meter cube per second. Okay. The next is the Gape resistance. This is the one of the important terms, because in the this gap, the minimum gap that we have to maintain between the workpiece and the tool, because the resistance is generated because of that only. Okay. So one thing is, that is h, that is gap is there, and the area gap means whatever the gap that we are using, or the surface area means if this is basically the workpiece and we have to create this kind of surface, means this material we have to remove. So that extra part over this wedge portion we have to make over the tool. Okay. So that whatever the surface area is there, that also we can say this surface area. Okay. So that gap can be balanced. So this basically the surface area, and r is represent as a specific resistance. Okay. That specific resistance is depends on what electrolyte we are using. Okay. So r, small r, is basically the function of electrolyte, that is specific resistance. H is the gap, minimum gap, and A is the area between the gap or the surface area, we can say. Okay. So please keep in mind this formula. Next is the density. Okay. Now here we are considering three things. First is, if it is first thing is, if it is a pure material. Okay. If it is a pure metal, means the material, the workpiece material which is given to you, if it is a pure material, then there is only one density, that is rho, means the density of that material only. Another thing is, if there is a alloy. Okay. If that alloy is made up of the two material, like two metal, that is 1 and 2, so it differently has density, that rho 1 and rho 2. That can be possibility. Okay. So what we have to do is, we have to individually calculate, means this, if it is individually given, that is rho 1 and rho 2 for the two metal, because the alloy which is made up of these, the combination of these two metal. So the density of these two metal are rho 1 and rho 2. So we have to calculate the equivalent density for using this rho 1 and rho 2. The second thing. Third thing is, uh, by the way, alloy is there, but in numerical problems sometimes it is given that the density is directly given to you of that alloy, so there is no need to calculate separate density for that. Okay. Equivalent density, because that is directly given to you. So these are the three things. Now in this formula what we are discussing is, if in case this two density or three densities or four density, means 3 4 5 6 metals, alloy which is made up of 3 4 5 6 metals, and the density of the individual metal is given to you, then how we will calculate this equivalent density? So for this only this formula is used. So this formula will be equals to 100. If I am calculating, if that density of the first metal, that is rho 1, and density of the second material, that is rho 2, for the third it's rho 3, and the like three metals are there, 100% of that metal, of that alloy is made up of x percentage, x1 percentage which is the density of rho 1, x2 percentage we are using rho 2 density, and x3 percentage of the metal that we are using rho 3 density. So as per the percentage wide I'm using, if I'm writing, if it's given that 30% this and 30% this and 40% is this. So if you are directly using this 30 over here, then you have to write over here 100. Okay, if you are using 0.30 means in terms of dividing 100, then you have to write it here over 1. Okay, so that is already converted. So please keep in mind while in numerical calculation. Okay, so this is the formula for the equivalent density when it is a single density of the alloy is not given to you. Okay, if separate is given to you, then this is the formula through which you will calculate the equivalent density. Okay, next is the equivalence, that is electrochemical equivalence. Similarly, uh, the alloy is given to you, that is different metals, and the percentage for which x1 percentage is given to you, for that the atomic weight is a1 and valency is v1. For the x2 percentage, the atomic weight is a2 and valency is v2. For x3 it is a3 into v3, so on. So when you will see the formula for that, that is again 100 upon E equivalence equal to x1, that is percentage of that first alloy, into v1 upon a1 plus x2 into v2 upon a2, and so on. Okay, so this is the formula for the equivalent of electrochemical equivalence. Okay, if it is a by v is not for one material, means for the different material we are using in an alloy, then we have to put this formula as such. Okay, so this is the way through which we can calculate this electrochemical equivalence. Okay, the next is the flow analysis. The flow analysis is uh, used to define the flow rate. And as I told you that this flow rate is defined, means flow rate is defined that how much amount of the electrolysis that is moving. So when it is moving, because once the potential difference is created, means the heat is generated. So the heat generation is directly is given as hg. This is generation, heat generation is directly proportional to or equivalent to I square into r. I is the current and r is the uh, that resistance. Okay, and we can also write like we know that I v equals to ir, so I is equals to v by r. Okay, so that will be like v square by r also we can write. So there is no issue, but what the term is given to you, accordingly you can write this formula. Okay, so this is the heat generated, and the heat absorbed by the electrolyte, that is equal to q, that is flow rate into rho e, that is density. Now here it is not the density of the alloy or the metal, it is density of the electrolysis or the electrolyte. Okay, ce is the specific heat again of electrolyte. Okay, and tb is the boiling temperature of this electrolyte, and T naught is the ambient temperature or the atmospheric temperature of that electrolyte, or the process where this ECM operation is conducted. Okay, so this is T naught is the ambient temperature. What where these things belongs to, as I already told you these things, like Q is the flow rate of the electrolysis. This is calculated in cc per second. Rho e is the density of the electrolysis, and we have already discussed this thing. Okay, so this is the flow analysis. This is, and flow analysis can be conducted, and as I already told you that we are using this we are calculating this MRR or all these formulas for the 100% current efficiency, means whatever the heat is generated, that is directly proportional to or that is directly absorbed by the electrolyte. So that hg, that is equal to h in he. Okay, this I square r is equals to q into rho e into ce into tb minus t naught. Okay, so this is flow analysis. Next is the feed rate. Okay, so the feed rate is the nothing but it is a moment of the movement of the tool, which is basically what we are doing is to maintain a constant gape. As the constant gape is created, the material is start removing from the workpiece surface. If the material is removing, then the again the gap is increases. So what we can do is we can give a feed to the tool, so that that moves towards the workpiece. Okay, so that is that feed rate is directly proportional to the MRR, equal to the MRR upon the surface area, whatever the surface area is there or the gap area is there. Okay, so that is equal to MRR upon surface area. Okay, so in this video we are stopping up to here, and in the next video we'll discuss the numerical problems on the ECM. Thank you so much, guys.